Hello and welcome to another video. In this video we're going to be going over the problems from weekly contest 390, and I'm just going to go over all 4 of them in one video just to not make a billion videos. So let's start with this one, and if you have any questions about any particular one you can just fast forward in the video. So in the first one you're given a string s and you want to return the maximum length of the substring such that it contains at most 2 occurrences of each character. So you're given a substring and the answer here is this. And in the second one, it's AA. So there's kind of 2 ways you can do it. One's the brute force, which will still pass because I think for easy problems the constraint's like 100. So you can just say like for every starting index, let's just keep building as much as I can and then store that. So like if I start at B, for example, I will get maximum BCB. If I start at C, I will get CB. If I start at this B, I'll get this. If I start at this B over here, I will get this whole thing, which will be the best, and so on. Or you could just do a sliding window. So sliding window, pretty easy. You just keep adding characters, and your constraint to shrink the window is anytime a count of a character is more than 2. So whenever the count of a character is more than 2, you just keep shrinking from the window from the left. And that would also be pretty straightforward, and we can look at that for this example here. So if we have like B, C, B, 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 C, B, A. So let's just draw our window. So let's just keep drawing from the start. So far we only have a count of 2, and our result so far, the biggest we built is 3 characters. So here we have 3 B's, so we have to shrink from the left. So we will shrink like this. Then we keep going, so we have 3 B's again, so we have to shrink, so we shrink this off. And now we get a C over here, which is fine. Now we get a B over here, so we have to shrink again because we have 3 B's. And now finally we can add an A, so this will be our best. So pretty easy standard sliding window problem. Let's take a look at the code real quickly. So just hash map for the count of every character, left, result, and a super standard sliding window. You just increment the count of your character, and while the count of your current character is greater than 2, shrink the window. Then when the window is fine, just maximize the result. So pretty easy. I mean, obviously harder than a normal easy problem, but you know, pretty straightforward. And like I said, a brute force easily passes here too. Okay, so let's go to the next one. And I think this is the next one. Hopefully, there we go. And I don't know why I don't have like the examples, so let's just copy those in really quickly. So let's copy that in and copy this. I thought I had it. And ignore the code for a second. Okay. So the second one, and you're given a positive integer k, and you have an array equal to 1, and you can perform as many of the following operations on the array as many number of times. You can either increment the number by 1 or duplicate an element and add it to the end. Return the minimum number of operations required to make this possible. And the constraints here, I believe, is like 10 to the 5th. So in the first example, for k equals 11, you want the best result is 5. So you increment 1 to 4, and then you just duplicate it from there. So to increment 1 to 4, takes 3 operations, and then you have to duplicate it twice, so it's 5 total. So even if you can't figure out the optimal, it's kind of obvious to figure out that whatever, like what you're going to want to do is you're always going to want to increment first and then duplicate. Because like, let's say you have 1, it doesn't make sense to just like duplicate, and then all of a sudden increment this to like a 3 and then duplicate. Because duplicating at the end is always best. So that part's pretty intuitive. And you know that k is 10 to the 5th. So the max number of increments you can do, like let's say you're just like, okay, I'll just increment only. So if I start at 1 and I go to 10 to the 5th, then I will do 10 to the 5th minus 1 increments. And you can basically just run through all numbers 1 to 10 to the 5th and just figure out like, just like, I'll try every single number for my increments. And then whatever I try for my increments, I can figure out how many times I have to multiply for that number. So let's go through an example there. So let's say we have like 1 and our k is like 99 or something. And so, like I said, the most we can ever increment is 98 because it wouldn't make sense to do any more than that. But let's say we're looping like 0 to 98 or 1 to 98 or whatever. Let's say we choose to increment like 10 times. So basically what we would do is we'd say, okay, if we increment 10 times, we'd get 11. And then how many times do we have to multiply to get 99? So that part's pretty straightforward. You just do 99 divided by your number. And you would get 9. So you need 9 of them, and you start out with 1. So you would need 8 multiplications, and then you use 10 increments. And you can just do that for every single increment. So you can just loop from 1 to 98 for increments and calculate multiplications for each one, and then just figure out what's the minimum there. And also, obviously, it's not going to perfectly divide. So let's say we were trying to get 99 again, and we decide to increment like 8 times. Or not 8 times. Let's say we increment 7 times. So if we increment 7 times, our 1 will go to 8. And then we need to figure out like how many times does 8 go into here. So you want to make sure that like 8 times some number has to be this number or greater. So I think that's going to be like 104. So that's going to be 13. So you need 13 8s, and we have 1 8 to start off. So you need 12 8s. So you need to multiply 12 times and increment 7 times. So you would just get 19. And you can just like brute force every single combination possible, and that's like an O(n) solution. Because for any given number of increments, you can figure out how many multiplications you need in O(1), and you can just run through 1 to k of increments. Now, the trickier solution that I didn't find that some people did is there's like an optimization. So basically what you're doing is you start out with 1, and you increment it by some number. Let's call that like x. And then you take that number and you multiply it, and you have 1 of it already. Right? So you have, like, let's say I increment 1 to 8. So what this will be is I will increment 7 times to get 8. And then the multiply part is I will have 1 to begin with, and then I will multiply by y. So, for example, let's say we're trying to get 16 here. If x is 3 and y is 3, that means that we increment 1 to 4, and then we multiply it 3 more times. So then we'll get 4 times 4 equals 16. So you could do this for any number. So x is the number of additions, and y is multiplications. Then you're basically trying to minimize x plus y. And so if you're trying to minimize x plus y, and let's say you have some number of operations that you can do. Let's just say you have like 10 operations. How would you want to distribute it? So to maximize like the number you get with the minimum number of operations, you want these to be as close to each other as possible. Because let's give an example there. So if we have like 4 times 4, the numbers are exactly the same. We get 16. If we increment one and decrement the other, like 5 times 3, now we get 15. And then so on and so on. 6 times 2, we get 12, and so on. And that's the same for any square. So same thing, let's say like 10 times 10 is 100. But if we increment one and decrement the other, let's say like 9 times 11, we get 99, I think. So this is like always true. So basically you want your numbers as close to each other as possible. And now that you know that, the basic idea is we can have a k. So let's say k is like, let's just pick some random number, like 32. Because we want our numbers to be as close to each other as possible, we can just take the square root of k. And what we really want is like the square root of like the number that we would get us over k. So like the square root of k is going to be 5 point something, and we just round that up to 6. So we get 6 here. And then we basically figure out like, okay, in order to get 6, how many additions and multiplications do we need? Because we want our addition and multiplication to be basically the same. And if we go for a square root, we'll get like a perfect number. Because if we go for 36, then we go 1 to 6, which is 5 additions, and then we do 5 multiplications. So that's going to be like the best possible case, but this is going to be like what we're aiming for. And so basically here, you would figure that you would get like the square root, and then for the square root, you'd figure out how many additions and multiplications you need, right? Like that part's pretty straightforward because you know, like, okay, my square root is 6, so I'm trying to go 1 to 6, and then I need to get 36. Now, the only other thing is there might be a possibility where the number is such that it's smaller enough from the square root that you actually need one less operation. So let's say this number is 30. So we would do the square root thing. So we'd get 5 point something, round up to 6, and we'd be like, okay, well, to get 36, we need 5 additions and 5 multiplications. But because our number is only 30, we actually can like we don't need our last 6. So that's the last part of it, is you get the square root, and then whatever the square root is, you can subtract it from like the square. So like your square would be 36, and then you can subtract the square root and see if that number is bigger than or equal to k, then you need one less of your operations. And that's kind of the idea. So this works for any number. So let's just try one other number just to show this. So let's say our number is like 78. So basically we would try to get like the square root here and round up. So this would be 9. So we'd get 9. And then we figure out, okay, to get 9, we have to do 8 additions. And then our goal is to get 81. So in order to get 81, we have to do 8 multiplications as well. Like it's always going to be equal. And then for 81, so like this is to get 81, but is 78 9 smaller than 81? No, it's not. So we're going to need all 9 9s. But if instead of 78, if we had like 70, what is it? Like 70, then we'd be able to have one less of these. And it doesn't matter which one, because basically you would either do 7 times 8 or 8 times 7. So either one of those would be fine. So, yeah, because like it would either be 7 times 8 or 8 times 7, which is like the exact same thing. So that's kind of the idea of the shortcut. But if you like, the shortcut's kind of hard to figure out, but you can just basically brute force every number of additions and calculate out the multiplications. And that's what I did originally. But let's take a look at the shortcut. So we take our square root, we get the number of like that square root rounded up. Then if the square root times itself minus the square root is greater than or equal to k, right? Like for example, if we get, if our square root is 9 and our square is 81, if 81 minus 9 is greater than or equal to k, then we don't need that last one. So we would just do 2 times the square root minus 3, otherwise it's 2 times square root minus 2. The reason it's 2 times square root minus 2 or 2 times square root minus 1 or whatever is because this is like the formula. So like let's say this is 81. Our square root here would be 9. Or like, sorry, not square root would be 9. Each one of these would need to be 9. And because each one of these is 1 plus x and 1 plus y, that means it's 8 and 8. And if you need one less, then it would be 7 and 8. So that's why it's 2 times root minus 2 or 2 times root minus 3. So pretty straightforward. Okay, so let's do the next one. And let's do some deleting. Has some crazy rain, so sorry about that. I don't know how loud it is. Kind of annoying for sure. Rain in California in the spring, a little bit weird. Alright. Okay, so let's so here's the third one, I think. Yep. Okay. Let's make it a bit bigger. Okay. So the third one, so you have some IDs and you have a frequency array. And basically what you do at every single step is you take your number and you multiply it, or not you multiply, you add the frequency. And what you want to return is the maximum frequency of any number after each one of these operations. So if we take a look, what would happen here is basically like after the first operation, number 2 would have a frequency of 3. That's the only number, so we want to return 3. Then after the second operation, we do number 3, we add 2, so number 3 has a frequency of 2. Our biggest one is still 3, so we return 3. Then number 2 has a frequency of negative 3, so now number 2 has a frequency of 0, so our biggest is 2. So that's what we do, return. And then number 1 has a frequency of 1 for the last operation, so it would be this, so we'd want to return 2. I mean, it's the same thing for all of it. So the tricky thing is, like, it's pretty easy to figure out that you probably need, like, a priority queue. But the problem is, like, how do I have priority queue and update values, like, and make sure they're up to date? And the way to do that is because you're basically doing, like, the most updates you're ever doing is n, right? So even though some of your values might be outdated, it's fine because the most updates you're doing is n. If you were doing way more than that, it would be an issue. But because you're only doing n updates, what we can basically do is we can just have a hash map of our values, and we can just keep putting the new value into the priority queue. And when we get the max value, we can just check, like, is that max value the current value in our dictionary? And if it is, let's use it. And if not, we'll just pop it because it's an outdated value. So essentially, we'll have a bunch of outdated values in our heap, but it's fine because it'll still pass. It'll still be like the most values we're only putting in is O of n. So let's walk through that solution. And you have to do it that way. You have to keep putting in new values. You can't just like update an old value, because then there's problems. And there's like a lot of problems. Because there's some cases where like you put in one value and then you put in another value with the exact same count, and then you update like the second value first or something. It's like, how do you get to that? You can't. So let's walk through that solution with a heap where we just keep updating our values. So in the beginning, we can walk through all of the examples. So in the beginning, 2 would have a frequency of 3. So we would just put in our frequency and our number into the heap. And depending on the language, I'm just going to show this as a max heap. If you need a min, if you don't have a max heap, just put in negative numbers to get a min heap. That's fine too. Okay, so yeah, so we will put in just a frequency first, because that's the one we are sorting by, and then the number second. And if there's a tie between frequencies, we don't really care about the number. Like any one of those is fine. So because we're only interested in frequency. So 3, 2, we'll put this into the heap, and then this will be like. Then we just check, is our current biggest number up to date? So does 2 have a frequency of 3? Yes, it does. So it's up to date. So we will put 3 into the result. Then for the second operation, looks like the rain died down, thank God. Okay, so yeah, so for the second operation, 3 is a frequency of 2. So we will put that into the heap as well. So 2, 3, right? Frequency, then number. Then we just check, is this up to date? Yes, it is. So we will put in 3 again. Then for the third operation, 2 has a frequency of -3, so we subtract -3, so we get 0 here. So now we're going to put this value into the heap. So we will put it into the heap, so we'll put in 0, 3. This is like our fresh value. This should be 0, 2. This is our fresh value, and now this is outdated. So we can just check, okay, is this up to date? Does 2 have a frequency of 3? No, it doesn't, so this value is outdated. And we can just keep going through our heap, and as long as like the max value is outdated, we just keep popping until we get a fresh value. So we get rid of that, then we check, does 3 have a frequency of 2? Yes, it does. So this value is correct. So we're essentially going to put in values into the heap over and over and over, and some of them will be outdated, some of them won't be, and the ones that are outdated, we can just keep popping them until we have a fresh one. And we're guaranteed to have fresh values because, like, worst case scenario, we're going to put in a fresh value at every single stage. So here, this is our like result now. So we will put in 2 into our result. And finally, 1 with a frequency of 1. So we will put that into the heap. So that's going to go into, well, I guess the whole thing isn't sorted. So this is fine. And then we check, is this value still fresh? Yes. So we just put in 2 again. So that's the main trick, is you just use a heap and a dictionary, and you just keep putting in new values, and you just keep checking, is your value fresh, by comparing to the dictionary. So let's go through the other examples for that. So example 2. So 5 with a frequency of 2, put that into the heap. So 2, 5, remember frequency first because that's the one we're sorting by. So we check, is that fresh? Yes, it is. We just put it in, so we'll put in 2 here. Then 5 has a frequency of 0. Or I guess we actually just need to update in our dictionary. So update here, we will put in that value. So 0, 5. Check, is our biggest value fresh? No, it's not. It's outdated. So we pop it. Now we check, is this value fresh? Yes, it is. So we will store it. You can delete from like the dictionary if you want to as well. It doesn't really matter though. And then finally 3, frequency of 1. So that gets added to the heap. So 1, 3. And then we check, is it fresh? Yes, it is. So we will put in 1. And that's basically it. So it's a pretty straightforward algorithm. Honestly, the only tricky part is the how to keep the values fresh and how to do it fast enough. But once you get that concept, it's like very easy. So we can look at that one. Did I do in Python? Yeah. Okay. So yeah, pretty straightforward. You just have a heap and a dictionary. You keep updating the frequency, and then you just keep pushing the fresh values in. Because in Python there is no max heap, so I just use min heap. Putting in negative counts, pretty straightforward. Then I just have an infinite loop, and I just keep checking the biggest value. If the biggest value is up to date, then I use it and I break my infinite loop. Otherwise, I pop from the heap and I go to the next value and I just take the fresh one. And yeah, I guess I didn't go through like runtimes and stuff for the other ones, but for the first problem, it was kind of straightforward. Sliding into the second one was O of 1. This one is n log n because it's a heap, so honestly pretty straightforward as well. And yeah, and then like space, heap, and so on. I think all that stuff is pretty straightforward. Okay, so let's go look at the last one now. I do think this contest is like easier than most, so I think the person that finished it did it in like 8 minutes, so definitely easier than most. So let's take a look at this one. This one was also pretty straightforward, and there's two main ways, and I'll talk about them. So you have two arrays of strings, words container and words query. For each words query, you need to find a string in words container that has the longest common suffix. If there's two or more that share, then find the string that has the smallest in length. If there's two or more strings that are the smallest in length, find the one that occurred earlier. Return an array where you basically just return the indices. So let's go through the examples. So here's our words, and for our words query, so CD's in here, and in here. And so we want to return, first we want to return the word that is smallest in length, which is this one here, and there's no tie, so this is the one we should return, so we return one. Then for BCD, so this has BCD, this has BCD, this has BCD. We want to return the smallest in length again, so we return the middle one. So yeah. Then for the last one, so for XYZ, it doesn't share a suffix with anything. So because it doesn't share a suffix with anything, they basically tell you, oh, it's start raining again, fun. So they basically tell you that if there's no suffix shared with anything, you just return the smallest word in your words. So that's pretty straightforward. You can just like go through your words and figure out like what's the shortest word, which is this one over here. So that's why you return one. So let's go through the next one. So for GH, it shares it with all of them, and the shortest word is the last one. So you want to return 2. For this one, it's, what does it share? Let's see. So FGH is shared. I think that's the longest one. So you want to return 0. And then for A, C, B, F, E, G, H. So let's see. So I think the longest is GH, which is all of them. And then you just return the shortest, which is the last one. Yeah. So it's pretty easy to handle this condition here that the smallest in length and all this stuff. So smallest in length and earlier. And the way to do that is, like I said, there's kind of two main ways to do this problem. One is a string hashing, which I've done a lot of videos on string hashing. I think I'm going to make like an advanced DSA string hashing in-depth thing in the future, so you guys can take a look at that. I really like it, and I've used it a lot. But the more traditional way that most people do know is a try. So essentially, because we're comparing suffixes, all you have to do is just go through the word backwards and put it into your try. So let's go through this first example. So essentially, our try would just be like a root. And then as we're putting this word in, we're just going to put it in backwards. So we'll say like, okay, the root goes with the letter D here to a new try, and then goes with the letter C to a new try, and then goes with the letter B to a new try, and a letter A to a new try. And then same, so here it's DCB, same thing. Here it's DCB, same thing. And then this try also goes through X to a new try. Now the way to handle these things that are like all the smallest in length is actually pretty easy. So typically what you want to do is normally a try has some kind of like Boolean value, like is word or something like that. But instead of storing a Boolean, you can just store more information. So what we can do for our is word is we can store, so we can initialize it to like none or null or whatever. And we can just store the length of the word that was in here and the index of the word that was in here. And then when we are putting in more words, we can just check like, okay, is the word we're putting in shorter than the one in here? If it is, let's replace the length with this word, and let's make the index this word. And because we're going to be traversing our words, we're going to be putting in our words left to right. If we get to two words with the same length, we just don't want to put in the second one. So like, let's say we put in this word into our try, and then we try to put in this one in the same, like, and it goes into the exact same thing. we would just want to say that like this is the index we care about because they're both the same length and this one occurs first. So because we're automatically putting in words left to right, like the index part will get handled for us. So all we're looking for is shorter words that end up at the same node. And if a word is shorter that ends up at the same node, all we do is just record its length and its index. So I guess we can like fill out this try to show what I mean here. So, and also you do have to, you can handle this one of two ways. You can either have this same thing in the root, or because like if a word doesn't share anything with your current word, you can either have the same thing at the root, or you can just figure out like what's the shortest word, and then if your current word has no suffix with like the thing you're looking at, then you just return that one. But essentially, let's just briefly go through what that would look like. So when we're putting in like DCBA, so basically our root try, we're just going to say like, okay, there is no is word here, so we'll set it equal to the current word, which is 4 and index 0. Then the same thing here in all these, right? So this is going to be like 4 0 4 0. I won't have the array, I'll just have it like this because I made these a little too small. That's okay though. So 4 0 4 0 4 0. So that's what's going to be in the try, like the length of the word that was put in and the index. Then when we put in BCD for the second word, we're going to check, okay, for the root try, is this word bigger than the one we have in here? No, it's smaller, so that's the one we want. So we're going to replace this with length 3 and index 1. Same thing here. It is shorter, so we're going to replace it. So 3 index 1, and so this is DCB, so this will keep going all the way to, so 3 index 1, and all the way up to this section here. It's not going to go to the last one because it's only 3. So that's what's going to be at every single one of these tries now. It's like the best word that was in here is word of length 3 that ends, or that is at index 1. Then the A stays the same because there is no A here. Then for X, B, C, D, so the word that was in here is already better. It's already smaller, so we just keep that. So 3, 3, 1, and then now this X would be a word of length 4 and index 2. So now we can do the queries. So for CD, we're going to go backwards. So we can show it like this. So we're going to start like, and basically what we want is we want the index of the try that we can visit like the most, the furthest down. So we're going to go down this words query, and like the last try we visit, that's the index we store in the result. So we go to D, so we have a D, then we go to C, we have a C, and then there's no more letters, so this is the index we're going to store. So this is index 1 in our result. So let's actually delete this path so we can, there we go. Okay, now for BCD, so we're going to go backwards again to compare the suffix, so D, C, B, and now this is this, so index 1 again, so pretty easy. And then finally for X, X doesn't appear anywhere. And like I said, I just in my root try stored the length of the shortest word that was in the root, which is at index 1. So for X, it can't go down at all. So we'll just get to here. So we just put in 1. And that's our result. And you do the same thing for these bigger ones. I'm not going to go through that, but it's basically the same thing. So it's literally just can use a try. Or if you were to do string hashing, you can just keep adding to the hash and then have a dictionary of hash value and the index of where you saw it. And same kind of thing, if you run into the same hash value at multiple indices, just check the length of the word and store the shortest length. So store some kind of variable, maybe like the index and the length, and they'll be the exact same thing. So pretty straightforward problem. Let's take a look at the code for this one. And here it is. So we have our basic try. We get the length of the word. And then, like I said, if the word is none, then we just put in the length of the word that was in here and the index. Otherwise, if the length of the current word is smaller than the one that was stored in there, then we just update our word. And this is only for the root. You can do this another way. And then the exact same thing for other nodes. So I could have obviously organized this better before. Like I could have put this in another location, but it doesn't really matter. So there's like a little bit of duplicate code here and here, but it's the same kind of thing. So essentially, instead of just having a Boolean value for is it a word or not, you just store the length of the shortest word that was here and the index of where that word is. That way, when you go through your queries, you know exactly where the best word is because you have it stored already. So then, pretty straightforward. You just make a try. You go through your words. So first, you put all your words into the try by using this insert method. It depends how you want to make your try. You can just make it with an init. I usually like making a try with an insert method and just call it to put in everything into it. Then you can make another method if you want to like traverse the try with new words, but I didn't do that. So for every single word in the query, same thing. Go through backwards, start at the root, get the location, and just keep getting the location of the current try you're at. And if you can't go any further down, just break and put in the location where you were at. If you can go to the next try, just keep going down to the next try and keep updating your location. Then finally, when you couldn't go down anymore, just put the location, and the location is just the index in this current word variable into the result, and that's it. So pretty straightforward. This was a little slow. You can, like I said, you can definitely optimize it a little bit. Also, maybe prefix hash might run faster. Not sure, or like KMP or something. That could definitely work as well. And yeah, basically you needed something roughly like a roughly O of n for each word, and that's basically what a try lets you do, right? You just go down your try in your word, so it's roughly O of n for like each word. Or I guess not like O of n, but like for every character, you just go down and down into your try. So I guess the runtime would be like O of all the characters total. But yeah, pretty reasonable contest. And yeah, I think definitely decided to just clump all the solutions into one video so I wouldn't have to like spread it out, and I don't want to make like, especially for the days where there's 2 contests, I don't want to make like 10 videos. And this one was pretty straightforward. So let me know what you guys think. Let me know if you guys like this format, and yeah, hopefully this is helpful. And I'll see you next one. Thanks for watching.